Okay, so today we're going to start Chapter 6 of the Statics book. In Chapter 5, we dealt with rigid bodies. So the way we treated these bodies, for example, if we were to have a beam attached to a wall, is to take the beam and break it free. You know, I use this terminology a lot in class, from the rest of the universe, and then replace where it was connected physically to the rest of the universe by forces. So in two dimensions, we'd have a force here, and we'd also have a moment. Okay? So that's the way we handled things in Chapter 5. So this would be Chapter 5. So we take a rigid body, something that has volume, break it free from its surroundings, or rest of the universe is the terminology I use. And everywhere we kind of cut that piece free from the rest of the universe, we replace what's going on with these forces, and we call those the reactions. Chapter 3, we did something a little bit differently. In Chapter 3, we said, hey, look, I have a point, and perhaps there's a rope that goes over a pulley, and another rope that goes over another pulley here, and they're both connected at this point. And down here I have some weight, right? In Chapter 3, what we did is we also drew a free body diagram. So here's our free body diagram. Only this time we just drew a free body diagram of the point, right? And we replaced everything that was connected to the point with a force. Okay. And we noted that all of these forces actually acted along the ropes or the connections. Okay? So here's our free body diagram from Chapter 5. Here's our free body diagram from Chapter 3. And the next step in both cases was to write equations of equilibrium. So in both cases, we went to equations of equilibrium. So in Chapter 6, we're going to deal with systems that are a little more complicated. So in Chapter 6, we might have a system that's made from multiple members. So here's a member, right? So that's a rigid piece of metal. It's connected to this rigid piece of metal by a pin connection. It's connected to this piece of metal by another pin connection. Perhaps these two are connected by yet another pin connection. And finally we have, or not finally, we have another piece connected here, and then let's say we have a piece connected here, and another piece connected here, okay? And let's suppose that we have some force here, and down here we're connected to the earth by a pin again. And over here we just have a roller sitting, okay? If we look at this system, what we can recognize is we have a couple of choices. The first choice is we can go to each one of these pins. So let's call this pin A right here. So here's pin A. And we can draw a free body diagram just like we drew from Chapter 3 about pin A. Why is that? Because all of these members, right? All of these members can only apply a force in the same line as the member acts. So all of the forces that this member, and this member apply to point A must be along the lines of directions of those members. So one option is we could draw at point A these forces that look just like this. Okay? We could go down here to point B. So here's point A. Here's point B. And we can say, look, at point B we have these two members. Now, I have this member here, which is the same as this back up. I have this member that goes from B to A. It shows up right here in the A free body diagram. It would also show up in the B free body diagram. So there'd be a line right here. So here's the first thing we have to learn in Chapter 6. Is if this member is pulling on A, it must also be pulling on B. So we say in that case that the member is in tension. So if I drew this member pulling on A in this free body diagram, I must draw it pulling on B in this free body diagram. Now, I could have selected the opposite here, and I just would have had to continue on with that as I continue to draw free body diagrams. Here, let's call this point C. Now I also have a member from B to C. Let's pretend it's under tension, so I have a force here. Here I have a roller, so I have the reaction at the roller, which is just a force in the x direction. Let's go now down to point C. So here's point C. Right? This member, A to C, I drew as pulling on A, therefore it must be pulling on C. This member I drew as pulling on B, right here, so it must be pulling on C. I have two other members. I have a member here. I'll pretend that it's pulling. I have a member here. I'll pretend that it's pulling. We could go over to, let's call this point D over here. So now we have a free body diagram for point D. And give myself a little more space. Okay. So here's point D. Again, here's the A to D member. We're going to call that this way. I have this member, which I've already drawn in here, so I have to also draw that it's in tension. I have a member pulling down over here. I'll pretend I know that it's in tension. And finally, I have point E. So here's point E. I've already drawn that member, drew it in tension. I've already drawn this member. It shows up right here. I'll have to draw it in tension again. Now, E is a pin connection, so it can apply two forces. Here's a force, and here's a force, right? So let's go back and label these. So this force right here would be the AB force. This would be the AC force. This would be the AD force. This force right here, again, would be AB. This force is BC. We might call this BY for the reaction at B. Here's BC. Here's AC. Here is CD. Here is CE. And I forgot one thing. Let's say that this is force P. And so here would be, again, force P. Here is AD. Here is CD. Here is DE. Let's go down here. Here's CE. Here's DE. Here, let's call this EX. And here, let's call this EY. So, what do you think the next step is? The next step is equations of equilibrium for each free body diagram. You would be absolutely correct. So let's look here. So these free body diagrams are the same kind of free body diagrams we drew for chapter 3, right? So for each of these, we're only going to be able to write 2 equations of equilibrium. So we have 2, 4, 6, 8, 10. So here we have 10 equations that we can write, and I'm not going to write those. Let's count unknowns. We have AB, AD, and AC. So AB, AD, and AC. We have BC, then we have CD and CE, and we have DE. We also have BY, EY, and EX. So let's count. We're going to get 10 equations. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 unknowns. So now, very quickly, for something that's relatively simple, right? We very quickly get 10 equations and 10 unknowns. And what does this information give us? What it tells us is not only does it give us the reactions By, Ey, and Ex, but it tells us the forces inside each of these members, right? Now, we've drawn every one of these members in tension, right? If I calculate, for example, that the force in AB is a negative force, all that means is that it's not really in tension, it's in compression, okay? So here's method 1 that we'll use in chapter 6 to solve what we call trusses. So what's a truss? A truss is pin-connected. Truss is pin-connected members. And the second requirement, loads only at connections. Alright, so those are the 2 requirements for truss. Only pins are connecting these members, and the loads are only at those connections. If we have that, we can use this methodology, draw for every pin a free body diagram, assuming whether the member is in tension, as we've drawn here, or in compression. Write equations of equilibrium for each of those free body diagrams. So very quickly we get many equations. And then solve them for all of the unknowns. The unknowns include both the reactions and the forces in each of the members that are connected. This is called the method of joints. The reason we can use the method of joints for simple trusses is because simple trusses are pin-connected members and the loads are only at the pins, which means that all of these members are 2 force members. And we've talked about the fact previously that for a 2-force member, the force has to be directed along the same direction that the member is directed.